In this video, we solve problems 5 and 6 from the Differential Equations quiz number 6 during the spring 2021 semester. This is for elementary differential equations at Tulsa Community College. There were multiple versions of this quiz. These are the solutions for problems 5 and 6 in version A. 5 and 6 both cover standard L26, which is about the shifting theorems, also known as translation theorems, the unit step function, and convolution. So in this standard, we're not solving initial value problems, differential equations, integral equations, or integral differential equations. What we are doing is we're applying what we know about the shifting theorems, the unit step function, and convolution to compute the Laplace transform in the first place, or to compute the inverse Laplace transform. So in problem 5, we're given a piecewise function, and we're asked to use the definition of the Heaviside function and one of our shifting theorems to find the Laplace transform of f of t. And then you're given a hint. It says write f in terms of the Heaviside function and then apply one of the shifting theorems. So the first thing I would do is, as the hint says, write f in terms of the Heaviside function, or one of the Heaviside functions. Okay, so f has two pieces. It's a piecewise function. And if I want to write that in terms of the Heaviside function, the first thing I always do is I write the function that is on when t equals 0. So I'm thinking of this as turning the function 5t on at t equals 0. And the Heaviside function functions like an on-off switch. Remember, the Heaviside function at t minus a looks like this. As long as a is greater than 0, the Heaviside function gives us 0 until we get to a, and then at a, it jumps up to give us a 1. Sometimes this is called the unit step function. And when we multiply a function by this, it effectively turns it off until t equals a, and then at t equals a, it multiplies it by 1, so it turns it on. So initially, at t equals 0, this function at 5t is on, and I want to turn it off at t equals 2. To turn it off, turn y equals 5t off at t equals 2, I subtract the function, and then I multiply by the Heaviside function at t minus the time when I want to turn it off. And if you're saying to yourself, how does that turn it off? Let's think about it. On the interval from 0 to 2, in this case, our Heaviside function would look like this. It's 0 until we get to 2, and then it's 1 after 2. The value of the Heaviside function is 1 at t equals 2 or more. Okay. On the interval from 0 to 2, this Heaviside function is 0, so I just end up with 5t minus 5t times 0. So this is gone, and we just end up with the 5t, which is what we want on the interval from 0 to 2. But then at t equals 2, this function is 1, so from t equals 2 on, we'll have 5t minus 5t times 1. So subtracting that 5t there and multiplying it by 1 would give us 5t minus 5t, which is 0. So if we just left this like this would not be this function. It would be 5t on the interval from 0 to 2, and then it would be 0 the rest of the time, because we had a function that was on and we turned it off, t equals 2. But that's not what we want to do. We want to turn this function on at t equals 2. So we'll add that function times the Heaviside function at t equals 2. We're adding it because we're turning it on. And we're multiplying by the Heaviside function at t minus 2 because we're turning it on at t equals 2. So let's check and make sure that this actually checks out. If we're on the interval from 0 to 2, this guy is 0. So we'll have 5t minus 5t times 0 plus a different polynomial times 0. So that's 0 and that's 0, and we just get 5t on the interval from 0 to 2, which is exactly what we should get. It's exactly what we would expect. Now on the interval from 2 to infinity, the Heaviside function is 1. So this is 5t minus 5t times 1 plus this polynomial times 1. The 5t minus 5t, those cancel, and you're just left with the 2t minus 1, which is what we want. So this is f in terms of the Heaviside function. Since you've got two expressions involving the Heaviside function, I recommend simplifying. You can factor out the Heaviside function at t minus 2 there. So f of t is just this 5t. And then we've got 2t minus 1 minus 5t. So 2t minus 5t is going to give me a negative 3t. And we're subtracting 1 from that. And that's multiplying the Heaviside function at t minus 2. If you want, you could factor out the negative 1. It's up to you. I think I will. I think I like the look of this better. Okay. And now we'll just take the Laplace transform of each of these pieces, and that's the Laplace transform of f of t. So the Laplace transform is a linear operator, so it can just apply to each of these pieces. So I'll have 5 times the Laplace transform of t minus the Laplace transform of 3t plus 1 times the Heaviside function at t minus 2. Now for the first guy, we're going to use a very familiar Laplace transform formula. The Laplace transform of t to the n is n factorial over s to the n plus 1. If you don't remember that, you would just look it up in your table and you would see that t to the nth power has this transform. So this piece is pretty easy. You just bring the 5 down. You identify n. We're matching a pattern. N is equal to 1. And so then you substitute your n equals 1 into the right-hand side over here. So we'll have 1 factorial over s to the 1 plus 1, which is s squared. Now here we're matching a different pattern. Now let's look at our table. Notice we've got a function of t times the Heaviside function. Now in the table that I gave you, they're using u of t minus a for unit step function rather than h of t minus a, but u of t minus a and h of t minus a are the same thing. So it's just two different symbols that represent the same function. So we've got a function of t times a Heaviside function. Well, we can use either 52 or 53, but we only want to use 52 if the function looks like a function of t minus a. Or in other words, everywhere in your expression, rather than just having t's by themselves, you have t minus a's by themselves. And that's not what we have. We've got a t minus 2 over here, and I don't see any expressions involving t minus 2. So in that case, I think it's best to use number 53, which says the Laplace transformation, or the Laplace transform of g of t times h of t minus a is this guy. It's e to the negative as times the Laplace transform of g of t plus a. So we're going to use that over here. Okay, so in order to do that, the first thing we need to do is identify a and identify g. We've already identified g. If h of t minus 2 is h of t minus a, then a must be 2. Okay, and then we'll substitute into the left-hand side of this formula. We've got the inverse transform of e to the negative, or sorry, the Laplace transform of, g of t times h of t minus a is e to the negative as times the Laplace transform of g of t plus a. So now that we know we have our a here, we know that our a is 2, we can substitute into the left-hand side of that identity. I said left-hand side, I meant right-hand side. Okay, so according to that, this should be minus, bring the minus down, e to the negative as, where a is 2, so it's e to the negative 2s times Laplace transform of g of t plus 2. So we replace the t's with t plus 2's. That's what this says to do. That's easy enough. This actually tells us what to do next. So this says first compute g of t plus 2. And then once you know what g of t plus 2 is, compute its Laplace transform and of course simplify. Always a good idea to simplify. Well, if g of t is 3t plus 1, g of anything is 3 times whatever we started with plus 1, as long as that's in the domain, right? We're going to replace our t with a t plus 2. So I'm plugging in a t plus 2. I'm going to triple that, and I'll add 1 to it. And of course, we want to simplify. So we'll distribute our 3. We'll get 3t 3 times, and then a 3 times 2 there, which is 6, plus 1. So g of t plus 2 turns out to be 3t plus 7. Okay, so we have 5 over here over s squared, 1 factorial is of course 1, minus e to the negative 2s times the Laplace transform of 3t plus 7. And we have a rule for this piece and a rule for this piece. The Laplace transform of t to the n is n factorial over s to the n plus 1. The Laplace transform of 1 is 1 over s. So 5 over s squared here. Then here I would bring the 3 down and do some pattern matching. N equals 1. So I'll have 1 factorial over s to the 1 plus 1, which is 2. Plus, bring your 7 down, times the Laplace transform of 1, which is 1 over s. And that's not simplified. So you write those as fractions, multiply straight across, and you get this. So we'll end up with 3 over s squared here plus 7 over s over here. And that is the Laplace transform of f of t, which we're calling f of s. So that's the solution of problem 5. Now in problem 6, we're asked to, oops, it's a different problem. We're asked to evaluate a lot of different expressions. And we evaluate those expressions using the shifting theorems, the Heaviside function, the definition of convolution, and our table of Laplace transforms. So in part A, we're asked to compute this. Now, if we have this exact entry in the table, t times hyperbolic sine of kt, I would just apply that formula from the table. So let's go to our table and see what we have. We do have t times hyperbolic sine of kt. It's entry number 26 in the table. So it's this guy right here. Sorry, that's a mess. You get the idea. I'm going to clear that because I don't even like looking at it. But this is the Laplace transform. According to that, it's 2 times k times s over s squared minus k squared quantity squared. So the first thing that we need to do is identify k. K is the number multiplying t, so k is 4. And then this rule says we get 2 times k times s over s squared minus k squared quantity squared. So I've just used placeholder notation, just including parentheses everywhere where I intend to substitute in my k value. K is 4. So it's 2 times k times s over s squared minus k squared quantity squared. And then we'll just simplify. 2 times 4 is 8. And of course, 4 squared is 16. So that is the answer for part A. Happens to be really simple. And that's nice. It's nice when we get a simple one. Now for part B, we have the Laplace transform of an integral from 0 to t of e to the tau times cosine of t minus tau d tau. And as soon as I see that integral, I think of the convolution. So what I'm doing is I'm pattern matching this to the integral from 0 to t of f of tau times g of t minus tau d tau. That's defined to be the convolution of f with g. Like that's what this integral represents. That's the definition of the convolution. In order to do that, we need to identify f and identify g. So f is the function of tau alone. Well, I've got an e to the tau right there, and there are no other functions of tau alone. So f of tau is equal to e to the tau. And the function of t minus tau, it's g of t minus tau, that is our g. So g of t minus tau is cosine of t minus tau. Now, convolution is it's a function of t, and we typically denote it as a convolution of one function of t with another function of t. So we don't want to have f of tau and g of t minus tau over here. We want to have f of t and g of t. So we use these to infer what f of t and g of t would have to be. So if f of tau is e to the tau, this function takes its input and it says take e and raise it to that input power. So if I had a t here instead of a tau, I'd have f of t equals e to the t. So this is a convolution of e to the t with another function. Now over here, our input is t minus tau, and the output is cosine of t minus tau. So if we have some general input, question is, what are we doing to it? Whatever my input is, I'm taking the cosine of it. So stars are not obviously not in the domain. We don't typically use those as our variable. We usually use a t as the variable. So g of t must be cosine of t. So we have that right there. So with this one we just recognized from the table. With this one, we had to recognize it as a convolution. And then we had to identify f and g. And the next thing we do is we apply the convolution theorem. Which says the following. It says that the Laplace transform of a convolution is a product of the Laplace transform. So it's a Laplace transform of the first function times the Laplace transform of the second function. And this is e to the at with a equals 1, and this is a cosine of kt with k equals 1. So I'll just use my rules. The Laplace transform of e to the at is 1 over s minus a, and a is 1. So I'm substituting that in right there. And the Laplace transform of cosine of kt is s over s squared plus k squared. If k is 1, k squared is also 1. So we've got this fraction times that fraction, which tells me that the Laplace transform of our convolution, which is equivalent to what we started with, turns out to be s over s minus 1 times s squared plus 1. And that's it. We just took the Laplace transform of each piece. And then we multiplied. Okay, so that's A, that's B, and part C, I believe, asks us to compute an inverse transform. Last one, we have the inverse Laplace transform of 8s plus 3 over s squared times e to the negative 2s. Now, we've got an entry in our table that says this: the inverse transform of e to the negative as times f of s is this. It's f of t minus a times h of t minus a. Now, I always like to add in this intermediate step to help me get from here to here. What do I need to do? I need to find f of t. So I compute the inverse transform of f of s. That's giving me my f of t. Then I replace the t with t minus a. And then I multiply that by the Heaviside function at t minus a. So this is the intermediate step that gets me from there to there. All right, so here's my e to the negative as, and here's my f of s. Just the product has been reversed. A times b is the same as b times a if we're dealing with real numbers, so it's fine. Multiplication is commutative when we're dealing with real numbers. Even complex numbers too, that would be fine. So in order to use this, well, the first thing we need to do is identify a. And of course, you want to identify f of s. Well, if e to the negative 2s is e to the negative as, that means that a is 2. And then f of s, that's what we need to take the inverse transform of here to get f of t, is this. Now, the way it's written, we don't have a rule for that. But if we split this up into two pieces, because we have a single expression in the denominator, a monomial, we can take each of these pieces and divide by s squared and simplify, and then we will have rules for those individual pieces. So that is my f of s after splitting up that numerator. So one of the s's will reduce there. The inverse transform of that is f of t, and then we want to replace the t with t minus a, where a is 2. And then we want to multiply that result by the Heaviside function at t minus 2. Okay, so that's pretty easy, pretty straightforward. If you want, you could write that as 8 times 1 over s plus 3 times 1 over s squared. And then we take the inverse transform of each of these pieces separately. So I would get 8 from this piece, because the inverse transform of 1 over s is just 1, plus 3 times the inverse transform of 1 over s squared. So the rule that I'm using there is this one. It's a very familiar rule. And you have to be careful about that numerator. To figure out the number, that constant I need in the numerator, I have to infer what n is from the denominator. If n plus 1 is 2, that means n is equal to 1. So if n is 1, I need a 1 factorial in the numerator. So instead of leaving that 3 there, like I could have left the 3 there, but I wanted to factor out the 3 so that I would have a excuse me, 1 factorial in the numerator. So this is 1 factorial over s to the 1 plus 1, or 1 over s squared. And so the inverse transform will be t to the n, where n equals 1, so it'll be t. So we'll have a 3 times t from that piece. But we want to replace the t with t minus 2. And then we want to take all of that and we want to multiply by the Heaviside function at t minus 2. So we have 8 plus 3 times the quantity t minus 2 times h of t minus 2. And if you distribute, we'll have 3t minus 6 plus 8 is plus 2 times the Heaviside function at t minus 2. And so that is our answer. That is our f of t, if you want to give it a label. And if I want to, from here, I could write it as a piecewise function. Now you do not have to write it as a piecewise function, but it's a good habit to write functions that are written in terms of the Heaviside function as a piecewise function, because most people are comfortable with piecewise functions, whereas they might not remember what the Heaviside function means. And as your professor, I like to know that you really know what the Heaviside function means. So if you write it as a piecewise function, then I know that you really understand the Heaviside function. So the Heaviside function is 0 until we get to 2, and then at 2 it jumps up to 1. So this is splitting our interval from 0 to infinity into 2 intervals, the one interval from 0 to 2 and the other interval from 0 to infinity. So this will have 2 pieces. And we typically write the less than or equal to on the left side, that left limit, the lower limit. And on the interval from 0 to 2, this is 0. So we'll have this times 0, which is 0. And then on the interval from 2 to infinity, we have this times 1. And so that is another version of our answer. So let's see, what did we do here? We we basically did this. We said this is the same as the inverse transform of f of s. We simplified f of s so that we could take an inverse transform. And then the inverse transform of that's f of t, and then we replaced the t by t minus 2. And then we filled in the Heaviside function. So first we just went from this step to this step. And then we used this step to sort of tell us what to do next. So we computed this inverse transform. After simplification, we said the inverse transform of this is this. Then we replaced the t with t minus 2 and simplified, and we got here. And don't forget that h of t minus 2 that's multiplying it. So that's what we did. We said we identified those guys. We found f of t. We simplified the f of t minus a. And then, of course, multiply by the Heaviside function. And if you want to, it's just good practice to write that as a piecewise function. And that part's optional. So that is the end of our solution for problem number 6. And problems 5 and 6 are the problems covering standard L26. So if you do a reassessment over L26, remember you're going to have Laplace transforms involving shifting theorems, unit step functions, and convolution. And you will have inverse Laplace transforms involving those. And usually it's something like this with about 4 problems. The first problem, you're given a piecewise function and you're asked to find its Laplace transform by writing it in terms of the Heaviside function and then taking the transform, like we did in problem 5. And then problem 6 involves Laplace transforms and inverse Laplace transforms, where you would use your rules and your understanding of convolution, shifting theorems, and the unit step function in order to compute the transforms and inverse transforms. And when I say transforms and inverse transforms, I'm referring to Laplace transform every time.